Alright, welcome, and let's get started here in this first video. Before I get into the topic here of this first video, I want to go over a couple of things that you should be doing as you're watching these videos. First of all, make sure that you have your book, either the hard copy that I handed out in class, or you can even use the online textbook that I showed you. This, for example, was the online textbook there. You click on the table of contents and you can go to the particular section. In this case, we're covering section 1.1, so that's where I'll go so you can see what that looks like. And there are a number of different features that you certainly can use on this page here. Second thing, make sure that you've got your calculator handy so that you can actually type in some of the formulas and equations that I show you, so you actually get some practice using your calculator while you're going through these notes. And then lastly, make sure that you have pencil and paper or pen, whichever you prefer, to take notes. I expect that you are taking notes as you watch the video and that you come in the next day with those notes for me to actually view and see. So make sure that you're doing that. And the last thing I'd mention here with the video, of course, feel free to pause, stop, rewind, fast forward, whatever you need to do as you're watching the video. You're in control of this, and the power of this is really in your hands. So use it to help you understand fully what we're covering here. If there's something that you don't understand, go back and listen to it again. So with that, let's get started here in section 1.1. And actually, before we get started in section 1.1 here, I want to cover just briefly here the 4 topics of calculus. All year long, there are only 4 things we're going to talk about. These 4 topics of calculus. And a lot of the problems that we're going to see throughout the year are going to require that you're able to decode the problem, really, and understand exactly what each one of these 4 topics that they're asking you to use. And then finally, once you know that, you can then go back and try to solve that problem. But it first comes down to understanding which one of these 4 topics that they're asking you to find. And so the first one there is limits. And we'll cover each of these in more detail, obviously, throughout the year, so I'm not going to go into any detail about each one. I just want to tell you the 4 topics. The second is derivatives. The third topic there is definite integrals. And the 4th topic there is indefinite integrals. Those are the 4 topics that we will be covering throughout the year. And actually, this first chapter here is really an introduction into 2 of these topics, derivatives, and then definite integrals in the second one. So let's get started here in this first section. So section 1.1 is titled Instantaneous Rate. And the objective for this section is, given the equation of a function, estimate the instantaneous rate at a given point. That is going to be our objective there. And we'll go through the objective every time we go through one of these lessons, just so that you understand what is expected of you as you work through this section. All right, so with that, let's get started here in terms of what we need to know from this section. The first thing we need to understand is, what is a rate? The title of this section is Instantaneous Rate, so in particular, we've got to first understand what a rate is. Now, there are several ways that you can define what a rate is. I'm just going to start out with an example here, really. That one way to define a rate is it's a change in distance over a change in time. Think about when you're driving in your car, you look down the speedometer, and you see the speed that you're traveling. That speed is the rate that you're traveling. It's a change in distance or a change in time is really what it represents. If you're calculating after traveling somewhere, your average rate from point A to point B. You take the total distance divided by the total time. That gives you your average rate. Either way, you're doing the same basic idea. Examples of units that you might encounter then with a problem like that, you might end up with miles per hour, it might be feet per second, it might be meters per second. It just depends on the problem as to what units you might end up with in the end. All right, with that, let's jump into the rate that this section is titled on, which is instantaneous rate. Now, an instantaneous rate is the rate at a moment in time. A moment or an instant in time. That's the term instantaneous rate. So when you're driving in your car and you look down at the speedometer and it says that you're going 50 miles per hour, that is your instantaneous rate, your rate at this particular moment in time. Now again, we said that every topic that we're going to cover in here is going to come back to one of those 4 topics of calculus, so here we go. The instantaneous rate is actually another word that we use to describe a derivative. Sometimes they use the term instantaneous rate that's synonymous with derivative. Now, obviously, if we knew enough calculus, we could just simply start finding instantaneous rates or finding derivatives to answer questions like this. But we don't know enough yet, so we've got to think about some other ways that we can, in this case, approximate derivatives, and that is by using what's called an average rate. So an average rate is the rate over an interval of time. That's the difference between instantaneous versus average rate. Instantaneous, there is no change in time there. It's an instant, a moment of time. Versus with an average rate, it's over an interval of time. So some time has passed. So if we think about this, we could use this idea of an average rate to approximate an instantaneous rate by using smaller and smaller intervals to approximate that instantaneous rate. Take a smaller and smaller interval of time until you almost get that interval so small that it's basically an instant in time. 1/10 of a second down to 1/100th of a second, down to 1,000th of a second, and so forth. And keep making that interval smaller and smaller and smaller so that it almost becomes an instant in time. So that's the way we're going to approximate instantaneous rates, is by calculating average rates. So let's take a look at this example that they give you in the book. In fact, I'm going to flip back over here to the book just so you can see the example here. I don't know that I'll do this every time, but at the very beginning of this section, they describe a problem here for us that we're going to use for a couple of examples in this section. It starts right here in the first paragraph. It says, if you push open a door that has an automatic closer, it opens fast at first, slows down, stops, starts closing, and then slams shut. So just picture that door opening with an automatic closer and then coming shut on its own. As the door moves, the number of degrees D it is from its closed position depends on how many seconds it has been since you pushed it. So that's the premise here. That's the problem that we're looking at. So the question that we're going to ask is this. It says, suppose that a door is pushed open at time t equals 0 seconds, slammed shut again at t equals 7 seconds. While the door is in motion, assume that the number of degrees d from its closed position is modeled by this equation. D equals 200t times 2 to the negative t, for t between 0 and 7 seconds. And the question that they want us to answer here is, how fast is the door moving at the instant when t is equal to 1 second? Okay? So that's the door example problem with t equal to 1 second. So let me write down that equation that they gave us here. And they gave us an equation in terms of t, so I'm going to go ahead and keep it in terms of t here. In fact, I'm going to write more of a function notation for us here. So I'm going to write it as d of t is equal to 200 times t times 2 to the negative t is the equation they've given us. And that was for the interval from 0 to 7 seconds for t. So we're going to keep the domain there as well. And again, the question is, how fast is the door moving at the instant when t is equal to 1 second? It's not asking how far open is the door. If I actually plug in 1 second into this equation, d evaluated at t equals 1, would tell me how far the door is open. That's not what they're asking. They're asking how fast is the door moving at that point. So they're asking for a rate here. So the way that we're going to calculate this rate is by approximating it with instantaneous rates. So the idea here was to use an average rate on smaller and smaller intervals. And so that's what we're going to do. We're going to start out with t equals 0 seconds to, or excuse me, it's not 0 seconds. equals 1 second. That's the point they're asking us to use here. T equals 1 second to 1.1 seconds. So that'll be the first calculation that we use here. And again, we're going to calculate an average rate, so you can name it here, I guess, a number of things. I'm going to just use AR to describe this rate that we're calculating. That'll be our abbreviation for average rate. And we know that to calculate the rate, we start out with the rate is the change in the distance, in this case it's measured in degrees, over the change in time. So I just have to take the change in my angle that the door is open. That's going to be D evaluated at 1.1 minus D at 1 divided by the change in time. D at 1.1 minus D at 1 divided by 1.1 minus 1. That should give us a calculation of how fast the door is moving on that 0.1 second interval, from 1 second to 1.1 seconds. I'm going to do this because of the fact that we're going to actually have to repeat this process a couple of times. We're going to use our calculator here and punch in the equation into y1. And so grab your calculator and punch in the equation into y1. I already have it punched in there for us. And on your home screen, your calculator actually will evaluate a function using this function notation like you see that we have here in this problem. So what I'm going to do, I guess I'll try to move the calculator screen over here so you can see it. I'm going to, on the calculator screen, the home screen there, punch in that equation, except of course on my calculator I don't have a function called D. Instead I put it into a function called y1. So I'm going to do that exact calculation on the calculator here. So start with a parenthesis here and go to your variables menu, which is below your down arrow there. It says VARS. Find your variables under there. VARS is short for variables. Go over to Y variables and then function, and there's y1 sitting right there for us. And then put in 1.1. Just like we understand what D at 1.1 means in terms of function notation, your calculator understands what y1 at 1.1 means in terms of function notation. And then subtract, grab y1 again, evaluate it at 1, and we'll divide that by this interval. Now if you want to type in the difference like we have here on the board, you can do so, but I'm just going to calculate the difference and type that in. So 1.1 minus 1 is just 0.1, so we'll divide by 0.1. And we end up with 26.336. 26.336. And so that gives us an approximation that over that tenth of a second, the door was moving at an average rate of 26.336. I've rounded that to 3 decimal places. You need to make sure your answers, remember, are rounded to 3 decimal places. Yeah, next thing to consider is what are the units of this? Well, the way to determine the units of this, I go back to the calculation that we have here. We took D, which is measured in degrees, and divided by this difference in time, which is measured in seconds. So our answer here is actually in degrees per second. And you can see that just by looking at the calculation we did to make that calculation. All right, so that gives us an approximation. I'd like to make that approximation even better. We'll find out that actually 0.1 seconds is a pretty big interval for most functions that we consider. So let's make this time interval even smaller. So t equals 1 second to 1.01 seconds. And that's kind of what we're going to do here. Zoom in by a factor of 10 in essence on that interval and make it smaller and smaller and smaller. So again, our average rate that we're going to calculate is equal to D at 1.01 minus D at 1 divided by 1.01 minus 1. Now, it did take a little bit of time to punch that equation into your calculator the first time, but if you go back to your calculator, I can basically just simply bring up that last calculation by pressing second and then enter. And then using your arrow keys, I can go up here and on this 1.1, I can press second, and then your delete key is second insert to insert a 0 in there. Do the same thing down here for the value that we're dividing by, and just that quick I get the next calculation. So we get 30.234 in rounding, 3 decimal places. I'll go ahead and put units on this. Now normally we wouldn't worry about units on the problem until the very last step. We're going to say this is what this derivative is, or what the instantaneous rate is, and put units in our answer. But I'll just write it as we go here. And you can see there's quite a difference in those two values that we came up with. The goal here of this process is to come up with two values that we are comfortably, or that seem close enough that we're comfortable with. So going from 26.336 to 30.234 seems quite a significant jump there. So let's make that interval even smaller. Again, I'm trying to find two consecutive values here that are relatively close. So we'll go from t equals 1 second to 1.001 seconds. So your average rate is d at 1.001 minus d at 1 divided by 1.001 minus 1. Again, let's punch this into your calculator. And let's just quickly change that. Add in a couple of zeros. And you got yourself a calculation at 30.640. Again, I'll put the units on there. Now those are definitely much closer. The last two calculations there, 30.234 to 30.640. Now if we wanted to, we could go one step further with this to see that these are getting closer and closer to 30.6 or something like that. But generally speaking, if we get two answers like this, that's relatively close. I would say that sometimes you might even want to have that first decimal the same, but that's not too bad there. If you wanted to check to see if how close it was to the next one, you could just simply do that on your calculator. And just add a couple zeros in here and see how close it is to 30.64. You can see that it's definitely getting closer and closer to 30.6 or even 30.7, somewhere in there. But in general, what we do then at this point is we make a conclusion based on the work that we've made here. And we'd say that the instantaneous rate at t equals 1 second is approximately, remember again, we're approximating this, so it's not exactly this value. We know that there's going to be an error here, but it's approximately 30.640 degrees per second. We generally take the last calculation that we made and we use it to make our approximation for what we think the instantaneous rate is. Okay. Now if you stop and look at the calculation we've been doing here, in particular, I'll just take and circle this one here. You've seen that calculation many, many times actually. In fact, all the way back to algebra, you start seeing that calculation. We've really calculated here, but we're given a function, and we've calculated the change in that function over the change in time. The change in degrees over the change in time. It's really the change in our y values or the change in our x values. Change in y over change in x, difference of y over difference of x. It's better known as slope. This is just a slope that we were calculating here. So yeah, this first section that we're covering is really just a review of slope course. The only difference is that you get to pick the points that you're finding the slope on, and we keep making those 2 points closer and closer and closer and closer to each other. Okay? I guess the other thing I would note here as well for you, that if you're curious on what work is required for this, as you're doing this problem, you need to be writing down, first of all, what calculation it is that you are doing. That's that red box there. And you need to give me an answer that you found from that. Sometimes units are needed, and so I'll put the units in there as well. That's what I would expect to see in your work there. Okay. Let's take a look at the next example here. If you flip the page, actually, you'll see this next example. Same problem, but we're just going to change the time here. This is halfway down the page there that says do the same thing basically, but now at t equals 3 seconds. Okay? So we'll go through the same process, same function. I'm just going to go ahead and write the function down again for us so we have that right here. It was 200 times t times 2 to the negative t, and that was from 0 to 7 seconds. Alright, so now they're asking for at 3 seconds, so let's start out at t equals 3 seconds to t equals, now what we should have learned from the last example is that a tenth of a second, even though that sounds like a very short interval of time, we saw that it was significantly different from the other calculations. And generally speaking, a tenth of a second is probably too big of an interval for us to consider. So instead what I'm going to do is just jump past that and say, let's start at 3.01. Again, really all I'm looking for is to get two answers here, two consecutive answers that are relatively close. And until that happens, I'll keep going through this process. So the faster I can get to two consecutive answers, the better. Less work to do. So let's try that out and see what we end up with. So our average rate is equal to, again, it's a slope. Derivative, another word that we use to describe a derivative is its slope, the instantaneous rate. And it can be approximated with this average rate. So it's d evaluated at 3.01 minus d at 3 divided by 3.01 minus 3. So let's jump to our calculator and we'll just have it help us with that calculation here. Get rid of what we have up there, and I'll just go back to one of the initial values that I had through here. So 3.01 minus y1 at 3, and the difference in those values is 0.01. So there's the same calculation that we were doing before, it's just not at a different point. We get negative 26.979. Again, you can put degrees per second as you go through this problem, or you can wait till the very end. It's fine to wait. Let's try an interval that's a little bit smaller. So let's go from t equals 3 seconds to t equals 3.001 seconds. So our average rate turns out to be d at 3.001. Again, don't get lazy here with showing your work. Make sure you're showing this step every time. Write it out. Here's our calculation. And that's equal to, let's let our calculator do the work here for us. Let's change that equation there just slightly. We get a negative 26.985. Negative 26.985 degrees per second. Now that might look like it's heading to a nice number. It might look like it's heading towards a negative 27. It doesn't have to be that way. It doesn't have to be a nice number like we saw in the last problem. It was not heading to a nice number. This one is also true that it's not heading to a nice number, so don't jump to a conclusion that when it looks like it's heading to maybe an integer result, it must be. But again, let's write our concluding remarks here. These two answers are relatively close. I'm satisfied with those two results there. That the instantaneous rate, which I'm going to abbreviate here as IR, the instantaneous rate is approximately negative 26.985 degrees per second at t equals 3 seconds. Wrote it a little bit different this time here, just so you can see another way that you can write that answer out. It's fine to write it either way. One thing I did want to point out here, though, is notice that on this one here, we ended up with a negative. And that's interesting because the last problem that we just did, the answer, of course, ended up being a positive value. So the question might become then, well, why is it that one answer was positive, why was one answer negative in terms of what is the door doing? Well, one way that you could look at that is to go back to the graph of this function. I have this punched into y1, and I've got a window from 0 to 7 for my x's and a 0 to 120 for my y's. And if you graph this thing, you have a nice little curve that shows up like this. They show you that picture in the book as well. And you can trace this thing to, for example, t equals 1 second. And you'll see that at t equals 1 second, my graph is increasing there. The door is still opening. So if the door is still opening, I would expect that my rate would be positive because it has to keep increasing in value. A positive rate would keep increasing in value. If I jump to t equals 3 seconds, you can see that now I'm at a point where this door is starting to close. The function is decreasing there. So the sign here really is telling me something about the door. It's telling me the direction that the door is moving. Now, you can't always say that negative then means the door is closing and positive means the door is open. You gotta always go back to see how they're measuring this value of d. And if we just draw a quick sketch of what they showed us there in the book, remember that this was our door here, this was the angle d. I'll finish this out like this. That was the angle d. So if d is a positive rate, that means d would be increasing, which means the door would be opening. Versus in this case, if the rate was negative, that would mean that d is decreasing, which means the door is closing. That's as long as I'm measuring d this way. It could have been possible if they had said, they didn't say it this way, but it could have been possible if they said measure the angle between the door and the wall that it's opening up to. If that's the case, now as I look at this other option for d, as d is increasing, that means that the door would actually be closing. And as d is decreasing, that means the door is actually opening. So you always got to go back to the problem and see how are they measuring these things to figure out what it means. Okay? But in this case, the door is closing is what that indicates here. I guess we could go back to the previous example and say since it's a positive rate, we could even add a positive sign in front of this one here. That this is positive, so that means the door is open. Okay. All right. With that being said there, you have all the information that you need to know in order to answer the questions that you'll find on the website there. So check that out, and we'll cover those things in class. We'll go over those things tomorrow in class.